Hey folks, welcome back to my channel. In today's video, we will solve some IIT JAM previous year questions from quantum mechanics and atomic structure. So here is a question from JAM 2007. The question here asked the normalization constant A for the wave function psi phi is equal to A e to the power im phi, where the limit of angle phi is 0 to 2 pi is. Here we are given the four options. We have to find the correct one. So we are given a wave function defined over the angular range phi is equal to 0 to phi is equal to 2 pi, and we are asked to find the value of the constant a that normalizes the wave function. Let's break this down step by step. So step 1. So here in the question, what is given? The normalization of the wave function. The wave function is psi phi is equal to a e to the power I m phi, where limit of phi is 0 to 2 pi. This is our normalization condition, that is 0 to 2 pi psi phi square d phi is equal to 1. So to calculate psi phi square, what we have to do? We have to take the complex conjugate of psi phi, that is a star e to the power minus I m phi. So we get from here, that is a square, and apply it to the integral. We get integration 0 to 2 pi a square d phi is equal to mod a square integration 0 to 2 pi d phi is equal to mod a square into 2 pi. So using normalization condition, we get a square into 2 pi is equal to 1, where a square is equal to 1 by 2 pi. So after doing the square root, we get a is equal to 1 by root 2 pi. So that is our final answer, that is the normalization constant a is equal to 1 by root 2 pi. One more question from JAM 2008. Let's look at the question. If the electron were spin 3 by 2 particle instead of spin half, then the number of electrons that can be accommodated in a level are. The options are 2, 3, 4 or 5. So understand the question. Normally an electron has spin quantum number s is equal to half. This means it has two possible spin states. Ms is equal to plus half and ms is equal to minus half. So in each orbital we can fit two electrons, one with up spin and one with down spin. Now imagine what here the question has asked. The electron is spin 3 by 2 particle. So this is a hypothetical case. Suppose the electron had spin 3 by 2. Then what are the possible values of ms? Well, for any particle of spin s, the possible values of ms go from minus s to plus s in steps of 1. So for s is equal to 3 by 2, the possible ms values are ms is equal to minus 3 by 2, minus half and plus 3 by 2. That gives us 4 possible spins. This means 4 electrons can occupy the same orbital with a different spin state. So the number of electrons that can be accommodated in a level or orbital of the electron had spin 3 by 2 is 4. So the correct option is option C, that is our answer is 4. Here one more question from IIT JAM 2008. The question is, for a particle in a cubic box, the total number of quantum numbers needed to specify its states are 1, 3, 4 or 9. Let's begin with the basic concept. In quantum mechanics, a particle confined in a 3D box, also called an infinite potential well, has its energy levels quantized due to boundary conditions. When the box is cubic, all sides have equal length L, and the particle is free to move in three directions x, y, and z. In each direction x, y, and z, the allowed energy states are represented by a quantum number nx, ny, and nz. Each of these quantum numbers can take positive integers value 1, 2, 3, etc. These define the number of half wavelengths along each direction that fit into the box. So the total number of quantum numbers needed to specify a state in 3D is 3, one for each spatial dimension. Some students ask, should we also include spin quantum numbers? Not in this case. The question clearly asks for a particle in a cubic box and doesn't mention spin or electron or atom. So we assume a spinless particle and the question is purely about spatial quantum states. So we only need nx, ny, nz. That is 3 quantum numbers. So the correct answer is B, that is 3. 3 quantum numbers are needed to specify the state of a particle in a cubic box. Let's look at our next question. The question is, an electron is found in an orbital with one radial node and two angular nodes. Which orbital is it in? There are four options. We have to find out the correct one. Now, in atomic orbitals, the total number of nodes is given by n minus 1, where n is the principal quantum number. There are two types of nodes present in an atomic orbital. One is radial node, that is n minus l minus 1, and the other one is angular node. So the total node is equal to radial node plus angular node is equal to sum of these two, that is n minus 1, where n is the principal quantum number and l is the azimuthal quantum number. In this question, we are told that there are two types of node, one radial node and two angular node. So the total number of node is equal to 1 plus 2 is equal to 3, and we know that total number of node is equal to n minus 1. So n minus 1 is equal to 3, and we get from here that n is equal to 4. Also, angular node is equal to L is equal to 2. That means it is a d orbital, because when L is equal to 0, that is s orbital, L is equal to 1, that is p orbital, and L is equal to 2 is equal to d orbital. Now we know n is equal to 4 and L is equal to 2, that means that is d orbital. So the orbital is 4d. So the correct option is option D, that is 4d. So here is our next question. The question has asked, if psi is the eigenfunction to the Hamiltonian operator with alpha as the eigenvalue, then alpha must be positive, negative, and integer or real. So at first we have to know what is the Hamiltonian. In quantum mechanics, the Hamiltonian operator represents the total energy of a system. It is denoted as h hat, and when it acts on a wave function psi, we get h psi is equal to E psi. Here E is the eigenvalue and it represents the measurable energy of the quantum system. So in this question, they wrote the eigenvalue as alpha, but it is just another symbol for energy. What kind of values can energy take? Now we have to know. In quantum theory, one of the most important rule is the observables must have real values, because you cannot measure a complex number as energy. Since Hamiltonian is a Hermitian operator, its eigenvalues are always real numbers, never complex or imaginary. So the only guaranteed condition is that alpha must be real. It may be positive or negative depending on the system. Just like bound states in hydrogen atom have negative energy, but it must be real. So our correct answer is alpha must be real. Now our next question. A quantum mechanical particle of mass m free to rotate on the surface of a sphere of radius r is in the state with energy 10 h square by m r square. The degeneracy of the state is, we are given the four options. Now, a particle free to rotate on a spherical surface behaves like a rigid rotor, which we have already read in our quantum mechanics. Its energy levels are given by E is equal to L into L plus 1 into h square divided by 2mr square, where L is equal to angular momentum quantum number, 0, 1, 2, h is equal to Planck's constant, m is equal to mass of the particle, r is equal to radius of the sphere. Match with the given energy which they have given, that is 10 h square by mr square. We are given E is equal to 10 h square by mr square. Now we have to match with our energy equation, that is L into L plus 1 into h square divided by 2mr square. So if we set this equal, then we get the value of L is equal to 4, and we know the formula for degeneracy is equal to 2L plus 1. So the total degeneracy will be 9. That is our correct option is C. Now our next question. This is very important for JAM, NET, GATE, BARC and all other exams. So watch it carefully and watch how to solve these type of questions. We are given a wave function and we have to find out the number of radial nodes in the wave. So identify the radial part of the wave function. This is our first work. Let's break the wave function into two parts. Angular part is this sine theta cos phi. Anyone can easily find the angular part. That is, the angle is here theta and phi. So this is the angular part. and the rest of the part is our radial part. So our radial part is this. So we focus on this part only. We have no work with the angular part because we have to find out only the radial node. So radial nodes are the values of r except at 0 and infinity where the radial part becomes 0. So we have to find the value of r where the radial part becomes 0. So at first take r by a0 is equal to x, then put it into the equation, that is 2x minus x square is equal to 0. Then we can get two values of x, one is x is equal to 0 and the other one is x is equal to 2. Now as we know, at x is equal to 0 the value of r is equal to 0, that is the origin, and origin is never a node. So we have only one solution except x is equal to 0, that is x is equal to 2, and by putting x is equal to 2 we get r is equal to 2a0. So we can easily understand that we have only one node in the wave function, that is at r is equal to 2a0. So our correct option is option A, that is 1. Now our next question. This question was asked in JAM 2014. We all know how to solve this type of questions. Today we will know the trickiest way to solve this type of questions. So what is given here? Here in the right hand side we are given the kinetic energy term plus potential energy term into psi x, and the wave function is psi x is equal to e to the power minus ax square. This is a Gaussian and commonly seen in harmonic oscillator problems. So what is the trick? At first we have to remember the known result, that is the double derivative of e to the power minus ax square, that is minus 2 small a plus 4a square x square into e to the power minus ax square. Try to remember this, otherwise you have to double derivative e to the power minus ax square. Now we are taking our problem into two parts, and we are taking capital A as minus h square by 8 pi square m, and capital B is equal to h square a square by 2 pi square m. Then our left hand side becomes minus 2 small a capital A plus x square into 4 small a square capital A plus b into psi. Now in the right hand side there is no x square term. So to make this term omit, we have what to do? 4 small a square capital A plus capital B is equal to 0. Then we are getting b is equal to minus 4 small a square into capital A. Then the coefficient of psi gives us the value of c, that is small a divided by capital M. So this is the easiest and trickiest way to solve this type of problem. So try to remember this way how we solve this. And that brings us to the end of today's session. We discussed some beautiful jam questions from quantum mechanics, especially focusing on wave functions, eigenvalues, nodes, degeneracy, and more. If you have understood even a small part of this video, congratulations! You are building a solid conceptual base. In the next video, we will continue solving more interesting and conceptual problems from atomic structure and also pick questions from other important chapters relevant for JAM, NET, and GATE. So don't forget to like the video, share it with your friends, and subscribe to the channel Crack IIT Exams for more such targeted content. Till then, keep practicing and keep exploring the beauty of chemistry and quantum mechanics. Thank you for watching.